so much for inviting me, and thank you for coming. I know this is field season and your summer, and you have a lot of other things to do in January, so it's great to see you. And as I said, please feel free to interrupt me, to tell me I'm speaking too quickly, because I'm very presumptuous coming to your country and not speaking your language. So if anything is unclear or I'm speaking too fast, just let me know. So I'm going to be talking about a series of projects that I recently started, looking at trying to reconstruct population growth in South America and see what it can tell us about the interactions between human demography and our cultures and local environments. In particular, I'm interested in the last 20,000 years, which is a period of really rapid cultural change as well as climatic change. For example, this figure is probably familiar to many of you. During these last 20,000 years, this included the ending of the last glacial maximum, in which the sea levels dramatically increased as all the water that was in the glaciers melted, including rapid changes such as the California Channel Islands, when the northern set of islands went from being one large landmass to multiple separated islands, isolating populations, so you can see there are dramatic effects on the different populations. During the same time, this is the period during the peopling of the Americas, where the first people reached North and South America, reaching Monteverde by at least about 14,500 years ago, which is down here, kind of near the Portamonte area-ish. A little bit later during this time period, during the mid-Holocene, we'll call that maybe broadly 3,000 to 8,000 years ago. This was another period of really fluctuating climates, and there was a lot of geographic and temporal variation in how this affected different regions. So this is just a very small subset of examples, but each of these different circles and squares and triangles show a different regional effect of mid-Holocene climate change. And you can see that there's a lot of variation even within the same hemisphere on how a local population's either precipitation or temperature changed. So these are very local effects. At the same time, and overlapping with this, was one of the most profound times in human history, which is the rise of agriculture. And these dots indicate just a subset of areas, or at least the minimum number of areas where agriculture independently arose. And I'm going to focus a little bit in on South America and why it might not just be this one circle. But these, you can see two examples of really overlapping periods during the last 20,000 years of climatic and cultural change that affected and shaped human populations. There are a lot of different ways that human environments and cultures can interact, even from the choice of where humans choose to live and what kind of species that puts them in contact with. There are also things like in certain regions of the world after the last Pleistocene megafaunal extinction, that led to a decrease when all the large animals died out. There were way fewer large mammal domesticates in South America than anywhere else in the world, which is an environmental impact because like that cultural icon, there's no, for example, cow here that was a really stable source of milk because there was no animal to domesticate left after that extinction event. So my question here that I'm first trying to address is really, how did humans respond to these rapid changes during the last 20,000 years, both culturally and environmentally, and perhaps which is more important, or can they act together? And I'm going to use South America as a case study. So I don't need to convince anyone here that South America is inherently interesting, but I also want to make the point that it may be uniquely generalizable, that we can learn something by studying South America in particular about how humans behave in general. There are a few reasons for that. The first is that South America has a really interesting domestication history. So this is an image by Dolores Paperno, who mainly studies plant domestication, looking at identifying 4 different hotspots of domestication, and this is based on fossilized plant evidence that they've radiocarbon dated, for the most part radiocarbon dated. And they are largely between areas that weren't exchanging migrants in large numbers, so you see different plant domesticates in each of these different regions. So it's not like the European case where you see agriculture and sedentary societies for the most part originating in the Near East, and then taking that society structure and all its domesticates across the continent of Europe with them. Rather, we see these independent events starting much earlier than sedentary societies in South America, and rather independently. So this just gives you an idea of some of the crops, like the yams and peppers, that were domesticated in different areas, and these are mainly as supplements to hunter-gatherer lifestyles. As I alluded to before, South America is actually home to the largest megafaunal extinction event. So between 20 to say 50,000 years ago, across all continents, there was a mass extinction event of all the large fauna, all the large animals, and South America had actually the largest percentage of their animals die out. So this provides an interesting case study, as I said, that affected what later became animal domesticates, and this relationship of how humans may or may not have contributed to it is uniquely important in South America. And I'm just going to say actually that this project started as part of a consortium to study the megafauna, and the main question there being whether it was kind of climate or humans or some interaction between the two that led to their extinction events. And my main job is to reconstruct the human aspect in population growth to get at that question, but I'm not going to really come back to them yet. Importantly, and one of the things that makes South America such a great test case is that there's no evidence currently of really large-scale migrations and population replacements. For the most part, we think that once people entered from Central America, they entered from around a single point, somewhere either on the land bridge or probably on the water next to Panama, and they entered from this point and then spread out throughout the continent. Importantly, unlike almost all the other continents during this time period, there were no people already here. And there were, for example, this is in contrast to North America, which had later migrations, for example, 4,000 years ago, a large Inuit migration, or Europe, where there are multiple population replacements during the last 10,000 years, both from the Near East and from the Russian steppe. And there are already like older human groups, such as the Neanderthals there, when humans entered. So that means that South America is a good case study to understand how humans behave and interact with the environment when they enter kind of an open space that is uninhabited. In particular, I'm going to try and reconstruct human growth rates over space and over time during the peopling of South America, to explore questions about these human expansion dynamics in general. So that question of what happens when humans enter a new space, and look at the demographic consequences of climatic change and domestication in the context of changing demography, which I'm really referring to changing population size over time. And when I say the peopling of South America, I mean that very broadly. So I don't necessarily mean that first entrance of people, but over time people came to expand and really use all the resources and take over all of the land throughout the continent that we have today. So this is a very long definition over time. So to do this, my main data is going to be the distribution of radiocarbon dates. And I want to give a shout out to my collaborator, Alexis Mikhailu, and she is the joint first author on this work, and she really did the bulk of the data collection in terms of the literature review. So these are all published dates, excavated by people who are in this audience and throughout the continents and world. And the idea is that each radiocarbon date provides evidence of human presence at a specific time and a specific place. And so we can use this data and the distribution of humans over time and space to reconstruct their movement and population size. In particular, this database we also hope is a great resource for people working in South American archaeology or using it as a comparison case for other regions of the world. And so she read literature from Portuguese, Spanish, and English that's published in academic journals as well as radiocarbon. And we came up with a set of almost 5,500 radiocarbon dates located at over 1,100 individual sites. And I'm sure there are some that we might have missed, particularly those that are unpublished. And And so you can upload new dates if you have any to an open resource at my website, and that is maintained and open to the public that anyone can go and download the most up-to-date version rather than just going to the one that was published with the paper itself. So we encourage you to do that. And we use this cutoff that it's only dates that are older than 2,000 years in radiocarbon years, because we're really interested in that older time period up until the kind of starts to rise of agriculture. If you look more recent than that, then this number would also just explode. There's so much more recent material, but this is about an order of magnitude larger than the information that was available during this time period before. So what does this look like? So this is just a plot of all of our dates, and this is including some quality control to prevent oversampling. We have about 2,500 or 2,600 what we call independent dates out of the 1,100 sites. You can also visualize this looking at the density, and you can see already that there's some variation in the density spatially. And part of this is actually true that there were different numbers of people in different areas, but part of this is that we don't have great coverage for all the regions. And in particular, I'll give a case study of the Amazon where radiocarbon dates and archaeological materials just very unlikely to be found. So we're not claiming that the absence of dates here means that there weren't humans. It's really that this is not the right type of data to get at that question. Phrased in another way is the absence of evidence is not evidence of absence. So we're really focusing here on the regions that we do have good coverage, which is mainly along the coasts, to get kind of a continental scale picture, and then we'll talk about a regional scale picture as well. I briefly mentioned some quality control. So the first question that always comes up when using these radiocarbon dates as data is what about oversampling? One researcher just has more money to do radiocarbon dates than some others, so maybe that leads to an increase at their particular site. So we do take some controls where we only take one site or one date per 200-year interval per site, and these have been established in the literature for a long time now. So I'm going to talk a little bit about how we translate this data into estimates of human population growth, and I'm going to first take, as I said, a continental view to look at that first question of what happens when humans expand into an unoccupied territory and how does their environment affect that. And then I'll take a look at the regional patterns. So this is not new to people in this audience, but the idea of calibration and a radiocarbon date. So when you get a radiocarbon date, you get this C14 date. It has a mean and then a normally distributed distribution with some known error. You use the ratio of C14 in the atmosphere over time to create this calibration curve through which you get a distribution of calendar dates. So your calendar dates are not a specific point in time, but rather this probability distribution of when the date likely occurred in calendar years, like the years that we have today. And this is just from Oxcal, an example, using 10,000 years ago. And I use the Southern Hemisphere curve for all of my calibrations. So before we look at that, we can look at just a histogram of the dates over time. And these are taking the median of those distributions and plotting for all of the sites those independent dates after quality control. And we can start to see some general patterns emerge with entrance of humans and kind of a rapid expansion. Something unclear going on here. There may be some increases or decreases. We don't want to interpret that yet. And then a rapid expansion kind of unidirectionally afterwards. But as I said, we lose a lot of information about the distribution and uncertainty of the dates by looking at these dates as only one point in time. So we want to use a method that will allow us to capture this uncertainty. So instead, we're going to use something called these sum-probability curves. Oh, wrong direction. Which is taking the convolution of all of these independent distributions. And this has been used before in Europe and North America and Australia. And even in regional scale studies from people at this university within South America itself. And this just adds up all of those individual dates distributions into one large distribution that captures the uncertainty over and the density of the material over all of those 2,600 dates. So a little bit more about this method. Importantly, it assumes that the amount of material that we have dated is proportional to the amount that's left, which may or may not be true because of taphonomic processes or funding, things like that. But it also assumes that the amount of material that a population leaves is proportional to its population size. For example, there can be issues with interpretation because certain increases or decreases, these peaks and troughs, can be caused by fluctuations in the calibration curve itself, and uneven sampling in time and space, with trying to balance these understanding regional variations with having large enough samples to draw important conclusions. Though there is reason to be hopeful, importantly that there's a lot of evidence that these SCPDs, these probability curves, really do mirror actual processes. They are highly correlated with kind of long-term used measures of population sizes, such as the number of sites or the number of burials and structures, as well as land use measures related to pollen in an area. There's also extensive history over the last, say, 5 years, simulating data and understanding how these distributions work, minimum sample sizes, and how fluctuations can affect their interpretation. And we try to actively control for some of the limitations I mentioned by talking about really large sample sizes and making inferences over long time scales. So to kind of summarize this tool, it's a useful tool, particularly for looking at these high-level patterns, but we have to be careful about over-interpretation on small timescales or tight geographical regions. So this is kind of ideal when we're talking about these large continental or large regional patterns over from 2,000 to 14,000 years ago, which is the time period that we're interested in. So what does it look like for South America? So this is very similar to the histogram, but it incorporates this uncertainty in our date distributions. So the gray line in the background is the raw data, and then we have just a 400-year moving average in this black line as to prevent over-interpretation. The real problem is, so this is a kind of established method that, as I said, has been used to study continental patterns around the world. But one thing we wanted to do is say, now that we have this, how do we actually interpret it? Can we say anything quantitative from this data itself? And to do that, we're going to fit a statistical model and come up with some new methods. So the first thing that we do is we sample a random set of 2,600 dates. It's actually 2,576, the same number of dates that we have in the original population. But it incorporates more uncertainty by taking a random sample from this distribution rather than just using the median or the mean of each individual calibrated date. So this is just our random sample from that probability density curve, and so we get this vector of number of dates. And as I said, this includes more of the variation and uncertainty in the radiocarbon dates than using just the median. For example, like we did with the histogram before. And then what do we do with this? Well, we fit various models. So just to walk you through it, this is the likelihood function for exponential population growth, or if you look at that curve, just fitting an exponential equation. And this is logistic growth, which I'll show you a picture of what that looks like, but it's kind of that S-shaped growth. So we take each of these xi's and we put in our random sample, and then we can multiply all of those different independent events and get a likelihood and parameter estimates for what that growth would have been. And we try that for a series of a lot of different models, so all different pairwise and piecewise examples of exponential and logistic growth in 500-year bins, and this is our best fit model. So this gives us a way to really interpret all the squiggles on the SCPD without overfitting to those squiggles, which might be calibration artifacts. So what the best fit model is logistic growth from 14,000 years ago until about 5,500 years ago, and then exponential growth until 2,000 years ago. And one point that I want to make is this change point is a parameter, like when you shift from logistic growth to exponential growth, and the likelihood surface is fairly flat there, so we estimate reasonably the same likelihood for anywhere in this time interval. So between about 4,000 years ago, close to 6,000 years ago. And that's a really interesting time period in South American history, which I'll talk a little bit more about later. Just to mention, there are a few other models that we tested, for example, a single phase of exponential growth, multiple phases of exponential growth, or logistic growth over time. And then we compared these using the Bayesian information criteria based on their likelihoods under this new likelihood method that we developed, as well inferring the parameter of when the changes occurred and the parameters of those models, like the growth. We also did another test to say if we can really tell the difference, if this is really two different epochs of history. So can you say that the logistic growth is quantitatively different than the exponential growth and not just like that visual fit? So we do this by plotting the density of the material, so that y-axis before, versus the change in density over time. So if you think back to like physics, this is like plotting position versus velocity. So it's a quantity versus the rate of change of that quantity. And you see two different time periods colored by the plot before. So the first epoch, logistic growth, all the dots are in red, and we get this linear fit, this statistically significant linear regression line with a negative slope. So density, this is basically density dependent growth. So all this red line is saying that the higher the density of your population, the slower the growth rate in the population. Versus for the blue epoch, which we saw before, this is basically flat. It's not significant. This p-value is not significant. You can't say it's different from just a flat line, and that's non-density dependent growth. And this is consistent with having two epochs, the first of logistic or density dependent growth, and the second of exponential growth, where the population is growing at the same rate no matter how many individuals they are. So this is an independent test for having two different epochs. So we're going to interpret this as saying that humans actually, or our interpretation of this is saying that humans are bounded by resources too. Particularly during that first time period, this density-dependent growth is saying that there is a set like population level or carrying capacity, as it's often referred to, that humans can reach. And as we start to reach that level or number of individuals, our growth rate slows. And so that is very characteristic of animal populations throughout the world. So that logistic S-shaped growth is seen when almost any bacteria or plant or mammal invades a new area that is uninhabited and they don't have any competitors. So up until about 4,000 to 6,000 years ago, humans are behaving like almost any other animal, even bacteria, on the planet. And that's surprising given that humans like to think that we are very unique. And as recently as 5,000 years ago, we weren't, and we were limited by the carrying capacity of the local environments. And this is also noticeable that that flat period where we're approximately at carrying capacity lasted for about 4,000 years. If you remember back to like this period here, where there isn't really much population growth going on. From this model, another nice feature, aside from looking at the just general shapes of growth over time, we can also actually get specific quantitative growth rates of human populations. So we find initial growth to be really rapid, so that's this period over here, and this is plotting the growth rate over time, where it's about 3.5% growth per generation, which means that the population doubles in South America approximately every 20 years. Importantly, there's no net increase from about 9,000 to about 5,500. And then there's renewed exponential growth, this blue component, of about 0.6% per generation. And to put this in context, that 3.5% per generation is about an order of magnitude larger than the same time period in like the Near East and Europe. So this is suggesting that South American growth rates were much, much more rapid than everywhere else. And one reason to think that that's true is that we're entering a completely uninhabited land that has a lot of resources that humans can exploit and grow very rapidly. And there are very low population numbers at this time. So based on, for example, genetic evidence, people assume an effective population size of just 100 to 200 or so individuals entering the Americas. Census sizes are obviously much bigger than that, though. Notably, more than half of the growth occurs in this last phase from about 5,500 until 2,000 years ago. And this kind of dotted line is kind of indicative of what I'm calling the carrying capacity. So this last phase, in the last 3,000 years that we're interested in, really more than doubles the population. Importantly, you can compare this to environmental data. So here we're looking at two proxies from ice cores, one from Antarctica and one from Bolivia. And there aren't any major, so in this light gray scale is when our likelihood estimates that change point occurs from logistic to exponential growth. There aren't any major global patterns emerging, at least at this point. We're going to take a little bit of a look at the regional patterns next that can explain this growth. What does occur during this time period, however, is large cultural change. So particularly in like Peru and Ecuador, you're starting to see the first really sedentary societies. And we know from European, Near Eastern populations that those have been previously associated with a really rapid increase in population size. One thing that we do see, however, in contrast to European societies where the first domestication events in sedentary societies or large-scale agriculture arose at the same time, that didn't happen in South America. I remember I talked a little bit before about having early domestication, a few stable crops, even way back here, starting 7,000 or 9,000 years ago in certain regions, supplementing hunter-gatherer lifestyles. So that really isn't enough to increase population size. You still get those kind of flat population sizes for thousands of years until there's a much more rapid cultural development, maybe 4,000 to 6,000 years in certain regions, and usually later in many other regions. I just want to zoom in for a second on that area that I've been calling carrying capacity, where humans are approximately stable, and see if there's something interesting going on. So one thing that's been known to be associated with agriculture as well is this idea of a boom and bust cycle, where populations initially take off because they have this stable food source, but there's either potentially poor nutrition because it's often some sort of grain base, or these large population densities are much better for spreading disease, so you get a decline in population. So we're going to test this by doing simulations, and we don't have to look at the details of the simulations, but I simulate a constant population size by assuming that people leave material randomly and uniformly. And you can create then 95% confidence intervals on what uniform distribution would look like. And so that is these gray dashed lines. So anything outside of these gray dashed lines, I think they're not actually 95%, I think they're 98% confidence intervals. Anything outside of those gray dashed lines would be statistically different than a uniform distribution. But this is hard to see. So there's, we see a few areas that are outside the lines, but this doesn't seem very convincing. But you do see a pattern where you're jumping from the upper bound to the lower bound successively. So upper bound to lower bound, just outside the significant threshold. And that is really unexpected. So instead of just looking at the bounds by date, because I'm going to look at actually the variance and how much this fluctuation happens. So variance is just how much the individual dates over time vary from their mean. And they're plotting a histogram of the 200 simulations of a uniform distribution. We get this null distribution of the variance for a uniform or constant population size. And our observed data is well outside the range that we see. So this is kind of suggestive evidence of potentially seeing these boom and bust, that these increases and decreases in population size, or at least the density of material, are statistically significant. They are real, and it's not just like, say, a calibration artifact or something like that. So to summarize this section, we can see three different phases emerge. From the initial entrance of people around 15,000 years ago to about 11,000 years ago, there's a really rapid expansion both spatially and temporally into new, uninhabited and resource-rich territory. We see this classic growth pattern through time that is seen throughout the animal kingdom. But about 9,000 or 6,000 years ago, there's this extended period of stasis, potentially boom and bust. This is a hypothesis that we should test further on a large, really continental scale. And this is interesting in terms of that complex domestication history, where we have, at this point in time, just a little bit of domesticated crops supplementing the diet of hunter-gatherers. Around 5,000 years ago, we see this really rapid renewed population growth, and this is where humans start to deviate from like the other animal models, where we really become the humans that we know today, where we are constantly kind of innovating our way out of our carrying capacities. And this mirrors shifts to growth that mirrors agricultural growth that's seen worldwide, but importantly differentiates these two factors of having these stable crops versus larger economic societies and systems. So I'm going to shift a little bit to talk about some really new work. So this is very preliminary and not finished, so I'm going to be much more hand-wavy and less specific, but I think it's important to look at kind of the regional variation that's going on because we know in all of these areas there's really different both levels or types of cultural developments and paleo environments. As I said, there's likely substantial regional variation both in the actual population growth that populations are over space, as well as local paleo environments. For example, we don't expect people in Patagonia to be experiencing the same environments as people in Atacama. And we also know from archaeological evidence that the timing of domestication events and the timing of other cultural events related to sedentism and societies occurs at different times in different places, and in some places not really at all. And we want to know if we can tease apart the relationship between the environment and cultural change, looking at a regional scale where they have these different effects. Does it affect the populations in different ways? So can we say that, can we tie like temporal changes in culture or environment to when that individual population starts to grow or doesn't? And as I said, this is very preliminary work, so we don't have a specific answer yet, but I'll talk through how we're trying to get at this and some preliminary results. So the first thing we want to look at, I'm going to look at these kernel density plots over the map of South America, where we have each of these points. This is going to be the location of our radiocarbon dates, and we basically throw a Gaussian distribution around it to smooth an area of where humans might have been. So the closer you are to the actual data point, the higher the density, and then overlapping sites that are near each other will overlap in their density, creating a higher density. So the closer together sites are, the higher the density. The more sites there are, the higher the density. So what does this look like in the context of South America? So we can do this by time slices. So these are sites that occur between 12,000 and 13,000 years ago calibrated. So KA is just thousands of years ago. And basically what you can interpret into this is that people are at very low population sizes and they're almost the same density throughout the continent. So once we really have evidence of people are everywhere. Exploring this more over time, we can see regional patterns in growth, where particularly at kind of known city centers in the old world, and particularly at coasts, you're starting to see really high densities of individuals and sites over time. One thing I'll point out, because we're nearby, is there's this kind of constant pattern it looks like in Patagonia of growth versus really extreme growth starting during this time period, for example in Peru. And these are consistent with what we know archaeologically. So to look at this in a little more detail, now that we can visually see that there are differences between regions, we want to quantify that. So we're going to split South America up into different regions, and we're going to do that without thinking about archaeology at all, because we want to know what happens in the archaeology. So my colleague that I mentioned before, Alexis, is looking at, she's an ecologist, and she made the regional determinations in collaboration with a number of paleontologists here in South America based on climatic zones and ocean circulation and vegetation biomes that existed in the paleo environment. So these, as I said, are not with respect to anything that we know about where humans were or what they were doing or any cultures about the humans. It's agnostic to all of that. And these are our main regions. Some of the sites are actually a little bit skewed because the projections of the two maps are off. But this is a good estimate of where the sites actually are. So each of the different regions is colored, and we have a large difference in the number of sites that we have between the regions. So we're only going to have, so this is the sample size and the number of dates per region. We're only going to be able to really look at our pattern, that probability distribution for ones that have at least like say 300 or 400 sites, and so that's going to be these 4 regions. So kind of Ecuador, Peru area, the northern Andes, central Andes, like Atacama area, Patagonia, and then like the Brazilian coast here. She looked a little bit at the Pampas at reconstructing the environment as well, but for most of the regions, there's just too few dates to be able to accurately say something. So what do the curves look like for each of these individual regions? So we have here the Peruvian region. We have, these are just colored to match. We have, oh, the axes disappeared. But it's the same thing where it goes from 14,000 years ago to 2,000 years ago through time, and they're matched to their colors. How are we on time? Are we running into the other today? Are we nervous about time? We can, okay, yeah, so I'll go quickly through this. So I just want to show that there are regional differences between the different areas. Most notably, the most and unsurprisingly, the most data-rich area from Peru looks a lot like our continental pattern, and that's consistent with a rise of agriculture in that time period during that we saw that shift. One thing that I want to draw your attention to is this really large appreciation in Brazil. As I said, the axes are missing. I think that's around 46,000 years ago, and this has been an observed effect, but we haven't had a large enough data set to really say if that was true or not. And we do see this kind of lack of people for an extended period of time, just an absence, and that correlates well to paleo environment. And so I'm not going to talk about, for the sake of time, how we reconstruct the paleo environment. So this is kind of the newest section, and we're trying to get kind of a continental, region by region, consistent comparison using pollen cores that have overlapping species between the different regions. And so my collaborator is going through and digitizing all the published pollen records for overlapping species and creating new age-depth models based on them, and then which look like this. And then you can create, using these different species, what the vegetation was in different regions at the time. The important part is that we're quantifying this using something called Bayesian change point analysis, which looks and provides a posterior probability of a change in vegetation during that time. So you scan along, if this dotted line is your pollen core, this gives you the posterior probability that something occurred. So there's this peak here where there's a change here. And so this gives us an output of a date that we can compare. Is that change point occurring at the same time that we infer a change point from our archaeological analyses in the human growth patterns? For example, this is what one result looks like. So you have the pollen core, then a smooth core, and then we infer a change point here. And then you can compare that to population growth over time. And so we want to know if population growth matches like the timing that we inferred that change point before, for example, from logistic growth to exponential in the continental pattern, but for each of these regional patterns of change point, does it match with, say, the first archaeological evidence of like sedentary populations and structures? Does it match that environmental change point that we're inferring? Or perhaps the first domestication event? There are other things you could match it to, but these are just a few of our hypotheses of what could cause a change in the population growth rate. And we say that our preliminary results are that this really varies by region. I'm not going to talk about the quantities because of time and because they're preliminary, but I want to go into one or two in particular. So, as I said, the first sedentary populations are really the most highly correlated in the northern Andes. This is like the Peruvian and Ecuadorian region, and this is consistent with what we saw in the continental patterns. However, we see a different story when we talk about that Brazilian coastal strip in Patagonia, where it's much more related to environmental change. And this makes sense given that in Patagonia, for example, you don't have a lot of these cultural processes in the same way. They really kept a much more like marine and hunter-gatherer subsistence strategy for a lot longer period of time than we're looking at. So taking a closer look at Brazil, again, the axes are missing. I think I made this on a Mac and now it's on a PC. But we see this really statistically significant through that same simulation process that I said, depreciation of people. And this coincides with really a dry period in time, and so that really supports an environmental hypothesis for what happened to these people. There's also evidence of a cultural shift in terms of the amount of shells and middens that are found and the amount of seafood that's eaten during this time period. There's a similar period which has been studied in this area, in mainly northern Chile. And so this curve looks fairly similar to what we saw before with kind of rapid growth, but if you separate it out into coastal and highland regions, you see a pattern that's been described by actually people who've worked here, Cesar Mendez, where there's growth in the coastal population. However, during its drying period in the middle Holocene, really lower population sizes, so a shift in the population sizes between these two really closely related regions. And what we think might be able to explain this is that the coastal populations, for example, like the Chinchorro, are really, really developed and maybe more able to buffer against climatic change that occurred at that time. And this is just a hypothesis that we're working to test now. So just to draw this into a conclusion, from the first section, that human expansion really follows this logistic growth seen in animal populations throughout the world until agriculture. And then you see this kind of sharp increase in population size again. I've started to describe the synergistic effect between climate and culture, particularly, for example, in that coastal area where earlier development of culture, for example, we saw in Peru and along the coast here in northern Chile, those populations didn't decrease in size when there was paleo-environmental change, particularly a drying, that decreased size in a lot of other cultures that might have been more dependent on the land. So this culture can help buffer against the environment. And with that, I want to thank you for listening. I want to mention that the first part that I talked about has been published, and thank my collaborators. So if you have any details, particularly about the methods there. I also want to thank all the archaeologists over the decades that have excavated and published these samples. It's the only way that we can really do the analysis that we did. I will mention that this is part of a larger working group to study the megafaunal extinctions in South America, and I'm reconstructing the human side of this. And this is actually a little out of date. Some of these people have graduated or moved, and there are new people involved in this. But yeah, most of them are paleontologists. There is lots of work still to do, but thank you.
Why, and if you're planning to extend that kind of estimations of population growth in more recent times?
So there's two real reasons that we chose around that time period. One is just logistics. So it's really difficult. There starts to be just a huge amount of data, and it tends to be a lot more biased that, people in certain regions have more funding and are publishing more. That's an area or time period people are really interested in, and the later, like the Incan period. But there's also, our main questions are really about what happened when people first entered, and by about 2,000 years ago, people were basically everywhere that they are today in the continent, so that won't really change the answer. We're also interested in the rise of agriculture, the starting of agriculture, and that gives us a little bit into that window. So we don't really have any current plans to extend that.
Okay, I have a question. How about the relationship between the evidence and the demography? Because to me it's not linear, right? So, especially if you compare ancient populations and the late populations, produce more things.
Mhm.
So the evidence will be more abundant over time. So how do you deal with that problem?
So that's also one of the reasons that we didn't do the later populations, is because they're going to have a really different subsistence strategy in the way that they leave materials. We tried to do some quality control filtering and binning of dates that are near each other. So as I said, we only take one date per 100-year window in an area. So hopefully that controls to some extent that people who, there's only one set of evidence going into our dates for each 200-year period. There will still be some effect, but hopefully not too much of an effect.
Okay, thank you very much.
Thanks.